Hello again, and welcome back to my channel. In one of my prior videos on this computer here, which is Carsten Herting's Minimal 64X4, I added a expansion card to it to create a speech synthesizer. Namely, I used a TMS 5220 speech synthesizer chip. And then I got it working with some of the built-in games that Carsten provides with the Minimal 64X4, namely the Space Invader style game. All of that worked great, right? And I was able to write the code in assembly in order to make it all work. However, that was pretty laborious. Using assembly is a very time-consuming approach to programming a computer. Now, I'm perfectly capable of doing it. I am a professional software engineer in my day job, so it wasn't a problem per se, but I would like to be able to do these kind of things at a higher level language. Fortunately, Carsten does provide a high-level scripting language for the Minimal 64X4 that he calls Min. It is inspired by Python, but it's not Python. It's a great little language, but I found it was limited in its ability to meet some needs that I had in order to work with some of the expansion cards that I was making. So, in this video, we're going to fix that. I am going to extend the Min language to a new language that I'm going to call Extended Min, and then apply this new language to interacting with my various expansion cards that I've already built for the Minimal 64X4. So stay with me, it's going to be fun. So what is this video really about? At a high level, there are three things. First, I want to discuss Min, the built-in scripting language that comes with the Minimal 64X4. I want to explain what it's good for, but also explain why it didn't meet my needs. Second, I want to talk about what I added on top of Min. As it was originally wrote by Carsten, Min is, well, minimal. That was the whole point of it. It is Python-like, but it's missing a lot of Python features. And I wanted to add some of these features, notably around memory management and lists and vectors, such that I could accomplish some of the things I wanted to accomplish with my cards. I will go through what features I added and why I added each of them. Third, I want to demonstrate that it actually accomplishes the goal. I would take the speech synthesizer drivers that I originally wrote in assembly and convert them to extended Min, and then demonstrate that it works, that I can actually control my speech synthesizer card through this language. There's also another project on the horizon that really motivated all this. Like, I didn't do this to simply rewrite the speech synthesizer drivers. There's a bigger project that I'm working towards that really justified the need for this. I'll go over some details in that project at the end of the video. Let me start with what was already there, because extended Min only makes sense in the context of the language it extends. Min is a small interpreted language that ships with the Minimal 64X4 system. Carsten introduced it on his channel back in 2022 in a series he called Computer Language from Scratch.
Let me introduce you to Min. Min is not Python, but it has Python-style indentation. It only features the statements if, else, while break, print, and define return. It has built-in functions like string conversion, user input, int conversion, length, key for non-blocking keyboard input, and random, yielding pseudo-random bytes. Min features local and global variables and one-dimensional arrays, string and integer data types, functions with parameters, and C-style ampersand referencing. Optional colon and semicolon syntax sugar, a double dot array slicing operator, and single quotes replacing Python's ORD function. So even though Min is not Python, if you know a bit of Python, you already know Min.
If you want to learn more about Min, I encourage you to watch the entire video. The link is also in the description. Keep in mind that Min is deliberately stripped down. Its syntax is inspired by Python, but as Carsten says, Min is not Python. Min runs on the Minimal 64X4 and was originally written in assembly. It lives entirely in RAM and gives you a real programmable environment, similar to BASIC was on old retro computers. That said, the analogy isn't exact. Min and BASIC are not the same thing. Min doesn't have any line numbers, it doesn't have goto, it doesn't have peek and poke and the kind of things that you would see in BASIC from the 1980s. Min is a great little language. The constraints that Carsten placed on it are part of the reason why it fits on the Minimal 64X4 in the first place. However, for the work I wanted to do with my expansion cards, I needed to add some more Python-like features to it. So here's my honest take. Carsten's min is not Python is exactly the right thing to do for what he was trying to accomplish, to create a simple scripting language for the minimal 64x4. Python is a big language, and trying to fit that all onto a TTL computer is just not the right goal. But the syntax is clean and it's well understood by programmers today, so it was a good choice. It was a good choice to actually use it as the inspiration for min. However, in Carsten's goal to keep it minimal, he excluded a bunch of features that I felt that I needed in order to do the kind of work that I needed to do. There are 3 features in particular that I wanted to add. First, 32-bit integers. As Carsten originally wrote min, he only supported 8-bit and 16-bit integers. For the kind of work that I want to do on the future project, not the current projects that I have, I needed 32-bit integer multiplication and addition and all the other kind of math operations. And so I needed to add that to the language. The second feature I wanted to add was large data buffers. Technically, as min was originally implemented, you can have an array of values. However, the way it was implemented, each individual value in the list that you're going to be assigning to an array are tokenized on their own. And when each of one of them are their own token within the interpreted language, they carry an overhead. And as a result of that approach to the design, you can't have very large arrays. I needed large arrays, not only for the speech synthesizer, but the future project that I keep on talking about. So I needed to re-implement how I can bring in large data buffers into the min memory space so that they can be operated on by the min language. And the third feature I needed was a richer set of vector operations. Once I had that large data buffer in the memory, I wanted to be able to manipulate it, and I wanted to be able to add to it, subtract to it, and navigate through the various values within it. Min does have some basic functionality in that regard, but I wanted richer features, things that are more akin to the list that you see inside of Python. Beyond those 3 features, there's a bunch of what I'll call syntactical sugar improvements that I made to the language, and I'll be going over those in detail. The final thing I wanted to do was to make it support the multiplier card that I actually talked about in a prior video of mine. The reason for this is for the future project, math and math operations will become important. And so I wanted to make sure that the min language, when it did multiplication and other math operations, it was using the faster hardware for doing that, as opposed to using a slower software implementation for the operation. Oh, one more thing. Why did I call it extended min? For those of you who are around in the 80s, and got a computer in the 80s, like a Commodore 64 or a TI-99 4A, you will recall that they usually had BASIC built into it. And usually there was an improved version of BASIC that you could buy and use in order to do more advanced programming. On the TI-99 4A, this improved version of BASIC was called Extended BASIC. That's me around 1986, sitting in front of my Texas Instruments 99 4A. I still have that machine actually. It sits in my home office right next to my daily driver Mac. The 99 4A shipped with TI BASIC and ROM, and it was perfectly usable. But if you wanted to do anything serious, you bought the TI Extended BASIC cartridge. Extended BASIC added the features the built-in language didn't have: subprograms, better string handling, sprite graphics, and faster execution. I spent lots of hours in my adolescence in front of that machine writing programs in Extended BASIC. And that same pattern played out in the other 8-bit platforms of the era. The Commodore had it, the Tandy, the Atari, and so on. They would all come with a built-in version of BASIC, and then later on, an improved version of BASIC would come along in the form of a cartridge or something, and it was called Extended BASIC. That's the convention I grew up with, and so here I'm using it over 40 years later in order to name the improvement to the built-in programming language on the Minimal 64x4. Extended Min. Before we get into the features, a quick word on how Extended Min was built. Like the original, Extended Min is written in Minimal 64x4 assembly and runs as a program on the machine itself. It's a tokenizer, a runtime, and a type system, all targeting the bare hardware. I built it using bespoke ASM. That is the configurable assembler I covered in detail in the prior video. Link to the repo is in the description. For this video, just know that bespoke ASM is what compiles the extended min source into the Intel hex file I downloaded to the Minimal64X4 over to UART, saved to flash as a program called xmin, and from then on run by typing xmin followed by a source file name. Files for the original min use the .min extension. Files written specifically for extended min use the .xmin extension. Most .min files will run unchanged in extended min. It's a strict superset with one deliberate exception that I'll get into. Now let's talk about what the language actually adds. Extended min adds 7 features to the min language. I'll show each one with a short code example and explain why it matters when you're writing code against hardware. Feature 1, the long type. Let me start with the one I mentioned first because it's really the reason why I started the extended min project in the first place. The original min has the char, which is an 8-bit unsigned, and int, which is a 16-bit signed. I found these types to be insufficient for the math of my future project, so extended min adds a long type, a 32-bit signed integer. Anything that needs to count past 32,000 now has a native type. This will allow me to directly deal with larger integer values up to about 2.1 billion. Feature 2, sized buffers with a memory-efficient way to declare large ones. This one was a foundational need for me, a space-efficient way to declare and work with data blobs. Without it, the kind of work I want to do on this machine doesn't really fit, so I want to spend a little extra time on it. In the original min, you could declare a sized buffer with a capacity in square brackets, and you could put an initializer right next to the declaration. For small buffers, it looked a little like this. This works fine for a handful of bytes, but the buffers I actually care about for hardware work are larger. Hundreds of bytes of LPC data for the speech synthesizer is a typical case, and some of my upcoming projects are larger than that. The problem that arises in min is that the values you assign to that buffer are each independently tokenized when min does the initial parsing of the script. Each token would carry with it an overhead, meaning that if I created a 100-byte buffer, the tokenized version would cost over 300 bytes. If I wanted to create large buffers, the original min would quickly run out of RAM. So I had to find another way to create large data buffers. Extended min introduces a separate syntax called a byte blob literal, written with a $sign in parentheses around the data. You can spread the data across as many lines as you want. No continuation markers are needed. The parser knows it's all one literal until the closing parentheses is seen. But the important part of this feature isn't the syntax. It's what happens under the hood. A $parentheses blob is tokenized as a length prefixed run of raw bytes. One length, then the bytes themselves, all packed together. That's dramatically less RAM during the execution. And on a 64 kilobyte machine, that difference is what makes it possible to declare large data tables in line with your source code. There's one more capability that comes with byte blobs, and it's one of the things I wanted most out of this update. You can declare a typed view on top of the same memory. View 16 and View 32 aren't copies. They are aliases that reinterpret the same bytes as 16-bit or 32-bit values in the little endian memory layout. You can lay out a binary structure as bytes once, and then read or write parts of it through whichever type that makes sense for the fields that you are touching. That's exactly the kind of memory layout control I wanted for the project I have in mind, and I'm pleased to have it working on this machine. The third feature is array length or size determination. Once you have sized buffers with initializers, you need a way to ask two different questions. How many elements are currently in the buffer, and how big is the buffer overall? Then, is the current count of elements within the buffer? Size of is its capacity. These are two different things, so they get two different functions. You can declare a buffer to be larger in terms of memory allocated than the number of elements that you initialize it with. This allows you to add more elements later. And that leads us into the next feature. The fourth new feature is dynamic list operations. This is one of my favorites because it's the feature that turns a buffer into an actual data structure. The append function adds a value to the end of an array and increments the count up until the buffer's memory size. Pop returns the last value and decrements the count, but it doesn't reduce the memory allocated to the buffer. It just reduces the number of elements in the array. Empty resets the count to 0 without touching the capacity. After calling empty, the array will have 0 elements, but it will maintain the original memory allocation. With those three operations, a sized buffer becomes a stack with no manual index tracking. If you have ever worked with lists in Python, you immediately recognize these operations. The main difference here is once allocated, the buffer's memory size becomes immutable, so you cannot append beyond the allocated size of the buffer. Extended min will raise an error if you try to do that. The fifth feature is compile time constants. In the original min, if you want to use a number to represent something, it's just a magic number in your source. There's no way to give it a name without using a runtime variable, which costs you memory you might not want to spend. Extended min adds compile time constants with the := operator. These get resolved when the source is tokenized. They don't exist at runtime. They don't take up any RAM, and they let you give meaningful names to every register address and command byte in the hardware driver. This can also be used to make name string-like constants, like banner text, error messages, and prompts. All of this allows extended min to have a better syntax for large programs, where constant values that you repeatedly use can be used by name rather than trying to remember that value, or if you have to change it later, trying to remember everywhere it was used and changing it appropriately. This is why constant values exist in other modern languages. The sixth feature is explicit casts. This is the one place where extended min is stricter than the original min. In the original min language, if you assign a 16-bit int to an 8-bit char, it silently throws away the upper byte. The program runs, you get garbage, and you spend an hour figuring out why. In extended min, that's an error. If you generally want to narrow a value, you use the cast operation explicitly. I want to be honest as to why I made this one decision differently. I've been programming professionally for well over 30 years, and I've had enough situations where a silently altered value has been the source of a bug and it's taken me forever to find it. I find that truncation of value or the other kinds of silent altering of values is the most reliable way to ship a bug that you will spend weeks trying to find. I've debugged this kind of problem enough times to be plainly allergic to it. And so I decided that I'm going to apply my programming sensibilities to how extended min will behave in these kind of scenarios. This is the one area where extended min isn't the perfect drop-in for min. In general, almost all min programs will run in extended min without alteration. However, if you have a min program where it is converting a 16-bit value to an 8-bit value, and in that conversion the value actually changes, extended min will refuse to do that. It will throw an error. If you still wanted to do that, then all you need to do is explicitly do a casting operation within extended min to acknowledge to the language that you know what you're doing, you do want that truncation, and then extended min will proceed as it would before. If you don't want that, then the error that you get from extended min is exactly what you should be getting. And the seventh feature is output not only to the screen, but also to the UART, or both. The original min has a print command, which displays string or values to the screen. That's it. Extended min has three output functions: print, serial, and output. The print function prints to the screen as in the original min. The serial function prints the string to the UART, and the output function prints them to both. This sounds minor until you're trying to debug a program that's also using the screen for its actual output. Being able to send debug messages out to the serial port without disturbing the display turns "I had to add print statements in squint" into "I just have a separate debug stream." There are a handful of smaller ergonomic conveniences too, like comma-separated initializers, the way constants and runtime variables share their type names, but those 7 are the headline features. Okay, here is my full Minimal 64 X4 setup. Here's the main computer as designed by Carsten Herting. This is my expansion backplane, which I designed myself. I have 3 cards in it. Here is the multiplier card from my last video. This is the speech synthesizer from about 2 videos ago. This is another card that will play more prominently in a future video. What it is a timer. It allows me to capture the exact time it took something to happen on the computer. It doesn't play a significant role in this particular video. I did use it to check how fast extended min was as compared to min. It is a little bit slower, but it's on par. And this card helped me show that, helped me optimize things and make sure that I kept it at nearly as fast as the original min. Remember, my goal with extended min is that I wanted the math operations it does to use the multiplier card. And what we are going to be demonstrating is extended min driving this speech synthesizer board to actually say something like this. This is the original assembly driver that I wrote for the speech synthesizer card. It does what it has to do. It sets up the I/O addresses for the FIFO buffer and the status register, send the speak external command, push LPC frame data into the FIFO byte, pull the buffer low flag, and keep feeding bytes until the phrase is done. It works, it's correct, but there's a lot to it, as you can see here. And here's the equivalent in extended min. Let me walk through it. At the top, I declare a bunch of compile time constants using the colon equals operator as we discussed previously in this video. I set up some addresses for accessing the card since the card is a memory mapped device. I've set up some commands that will get set to the card and a few masks that are going to be used to determine the meaning of various status bits within the card. The rest of this code does exactly the same thing as the assembly language version of the driver that I just showed you. In fact, the functions are one for one as you look at it. Let's compare this init function. This is the function that is used in order to set up the card when you first turn on the device or start engaging with it. What it does, conceptually, is it sets the internal pointers to the buffer that's being spoken to null, just to reset that. And then it goes through a reset sequence that is determined by the card. Once the reset sequence is done, we send the actual reset command and then wait until the card is ready to actually be used. Once it's ready, we're done. Now, in assembly, the exact same function is right here. This is the exact same function. It does the same thing as the extended min function that I just showed you. But as you can see, it's a bit more complicated. There's more going on, there's more instructions, and it's not obvious what any one of these lines are doing. You just saw the driver in both assembly and extended min. Now let's hear it play a sound. Let's check out one of the extended min scripts that I already have developed in order to play some speech sounds. This is the proverbial hello world in speech. So let's take a look at it. As you can see here at the beginning, I am importing the speech library, which you saw me go through in the previous scene. Then I declare some constants that will help make programming simpler and more understandable. You'll see me use them later. The first one, sysclear, is the operating system call for clearing the screen. The next one, sysprompt, is the operating system call in order to return to the actual command line prompt. kypos address is the variable that you have to set in order to change the location of the cursor. Then we get into the actual LPC data. Here, this is the hello world speech sound that you actually heard me play in my last video on the speech synthesizer. This is now encoded as a binary blob in extended min. You can see the use of the dollar parentheses notation that declares that this is a single binary blob to the tokenizer that extended min uses. I do declare the actual size. This is the precise size of the number of bytes of LPC data that follows. I can actually make it larger, but if I make it smaller, extended min will issue an error. Let's go through the LPC data. Then you see the actual code to actually play the sound. First, spinit, that's in the speech library. This initializes the speech synthesizer board. I call sysclear in order to clear the screen. Then I write some text to screen, hello world, just simple message. Then I play through the synchronous method the LPC data. This will call the methods that we just previously reviewed in order to run the actual LPC data through the speech synthesizer so I can hear a sound. And then when it's all done, I return to the system prompt. So we'll see this work. There we go. Much easier to use than writing that all in assembly. And that was the whole point of this project, is to create a high-level scripting language that I can use on the Minimal 64 that allow me to interface with my various hardware boards I'm developing much simpler than writing in assembly. Okay, that's it. I hope you liked what I showed you and you find extended min useful if you're using the Minimal 64X4. Everything I talked about, from the extended min implementation to bespoke ASM to my speech synthesizer card, are all available in my GitHub repository, all the links to which are down in the description. Now, I did mention this mysterious future project that I'm working on. I'm not ready to talk about all the details because plainly they're still in work, but what I'm trying to do is to expand upon the multiplier card that I talked about in my last video. I want to improve upon it. I want to turn it into a real processing unit that then can be used to accelerate various operations within the Minimal 64X4. So stay tuned. I'm sure I'll get this done sometime in the future. That's it for today. If you like this video, I'd appreciate it if you like it, and subscribe to the channel if you're not subscribed already. I like making these kind of projects, but they do come out slowly because, as I kind of alluded to earlier in this video, I do have a day job, so this is not something I do often. But if you'd like to see my next project when you subscribe, be sure to mark notifications so that you get notified when I do release my next video. Thanks for watching, happy hacking, and I'll see you in the next video.